Welcome back, everyone. This is a video that talks about KCL, and specifically I'm going to present a simple example that is going to focus on labeling nodes. When we talked about KCL, you might recall that we labeled nodes in a circuit as essential and non-essential, and I'd like to give you one specific example where we'll go ahead and study and label every single node in that circuit. So let's focus our attention on this particular circuit here. This is a circuit that has three devices, actually four devices, labeled anywhere from E1 to E4. And the blue dots essentially represent every part of the circuit that some of you may have labeled as a node. So there is node A, B, C, D, E, and F. And I would like to discuss with you right now which of those nodes are essential and which ones are not. First of all, I'd like to invite you to do this before you watch the rest of the video. So I'd like to give you an opportunity to pause the video and for each one of these nodes, write down if it's an essential node or a non-essential node. I hope you did that. If not, let's do it here together, and hopefully you can check your thinking as we're doing this. So first of all, let me start with node E. Node E is a node that is at the bottom of the circuit, and as you may recall from previous examples, typically this is a node where we assume as ground. This is a node where we assume that the voltage is 0. We don't have to make this assumption here, but this is simply a reminder for you that this would have been the typical scenario if this was a real problem that we were trying to solve. I also want to remind you that really nodes E and F are exactly the same. Why? Because they're connected with a short circuit. I just highlighted this with red. So once again, it doesn't matter that they are not physically placed on a piece of paper or on the slide at exactly the same physical point. The very fact that there is a short circuit between them guarantees identical voltage between E and F, guarantees, in other words, that the voltage in E will be the same as the voltage in F, and therefore, from an electrical perspective, those two physical points represent one electrical node. So if I wanted to do things correctly, I would not have given the F name. It would really be E. And for exactly the same arguments, node E is exactly the same as node D. So I would rather not label this a separate node, D. This really adds confusion, and it's really one and the same node. And following exactly the same logic, here's one more short circuit that essentially connects directly nodes C and D, making VC the same as VD, and therefore, once again, I don't like labeling this with an extra letter since it does not represent a different electrical connection. So now we're actually done with three of our points, C, D, E, and F, and let's focus our attention on A and B. Node A is a legitimate node, and by that I mean it's different than ground. But if I count how many devices are connected to node A, there is basically E1 and E2. And so this is a non-essential node in the sense that there are only two devices connected here. So I will label this as non-essential node. Finally, let's look at node B. Node B is right here. It's a legitimate node. There is no short circuit between this node and ground. And if I count the number of devices, I will have E2, I will have E4, and I will have E3. So this is really an essential node in the sense that I have exactly three devices, and anytime I have three devices or more, I have an essential node. So I hope you have enjoyed this example. I hope you have found this to be useful in your study, and we will see you next time.